All right, thank you. And a big thanks to the organizers for giving me the opportunity to present some of my research here. Today's talk is largely based on this paper with Tom Minkowski, but in the past year we've also done work on a very similar story in n=4 super young males. You will have heard a little bit about that in Russ's talk last week if you were there. And the goal of my talk today is to give you a complete understanding of ABJM integrands from the framework of positive geometries. And the specific positive geometries that we will discuss are what I call light cone geometries. Yeah. So I have a bit of a dual setup with, it will mainly be a Blackboard talk, but I will use the projector for images such as this on the right, which I'd rather not try to draw freehand. All right. So the outline is as follows. I'll first very briefly introduce the idea of positive geometries, and in particular, an important one, namely the ABJM momentum amplitude. I won't do this in too much detail, but I will introduce everything that you need to know for the rest of the talk. So even if you're unfamiliar with these concepts, you should be able to follow along just fine. And the second part is sort of the main part of the talk. We're going to be talking about positive geometries for loop integrands in ABJM theory. And we'll mainly be focusing on one loop integrands. And the way that we're going to be discussing those is by triangulating it in terms of chambers and fiber geometries. And these fiber geometries are the light cone geometries, which I refer to. And together with given a full classification of all the chambers, this will allow us to derive a neat and concise general formula for the one loop ABJM integrand. And in the end, if there is time left over, I would like to go over some of the story for higher loops. This is related to the notion of vibrations, which Russ talked about last week. And even though the main ideas are very similar to the one loop story, there are some interesting new structures that appear at higher loops, but we'll see how far we get. So first, let me tell you what I mean by a positive geometry. And I will call the positive geometry A, is a real oriented closed geometry with a canonical form which I will denote omega of A. Now these positive geometries and these canonical forms have to satisfy certain properties, but most of them won't be relevant for the talk today, so I won't go over them in detail. The most important part, which I will emphasize, is that the canonical form omega of A has logarithmic singularities at and only at the boundaries of our geometry. And it is this canonical form when you're talking about the amplitude, for example, or later in this story, which roughly corresponds to the scattering amplitude. So let's immediately, let's keep it up. Let's immediately jump into a very simple example. And that is a line segment where x is between A and B. So this line segment is our positive geometry A. And the canonical form of this positive geometry is given by d log x minus a minus the d log of x minus b. So it is clear that this differential form indeed has logarithmic singularities at the boundaries of a, namely when x is equal to a is one boundary and when x is equal to b. Now what if I had instead written down the d log of x minus a plus the d log of x minus b? If I'd written this down, I would still get a canonical form which has logarithmic singularities at when x is equal to a and when x is equal to b. But this cannot be the correct canonical form because this one also has singularities as x goes to infinity. And our geometry does not have a boundary at infinity, so we can't have a singularity there. And we can see that that is not the case for this differential form by writing it as a ratio. D log x minus a over x minus b. The fact that it can be written as such a ratio means that it won't have a pole at infinity. And this is a property which I will refer to as projective invariance. So we see that we can fix the relative sign between the terms, namely the minus sign rather than the plus sign, by requiring that the form is projectively invariant. Now there is one specific type of positive geometry which I want to draw your attention to, which we will encounter later. And that is those of simple geometries, or simple polytopes. So for those who don't know what a simple polytope is, it's a d-dimensional polytope where at each vertex there are exactly d facets. So example of three-dimensional simple polytopes which we will encounter are the tetrahedron and the cube, for example. And these simple polytopes allow for a very simple writing of their canonical form. Namely, for a simple polytope, the canonical form can be written as a sum over vertices. Some sign. And then we have the d log of all the facets at this vertex. Right? So these, what I call capital F1 through Fd, are the facets at the vertex V. And this relative sign, which appears in every term, can again be fixed by requiring projective invariance. So this is a very neat way that we can write down the canonical form of this type of simple polytopes. All right. So far, a very brief introduction on positive geometries, which highlights the main points which we will need later. Next, let me talk about what ABJM theory is and what the ABJM momentum amplitude is. So ABJM theory is a theory in three space-time dimensions of matter Chern-Simons. with n equals 6 supersymmetry. Now, most of these things won't be too important for the talk today. Really, the most important part of this definition is that it is three-dimensional. But there are a few properties of ABJM amplitudes which we will use later, which I'll briefly summarize. The first one is that scattering amplitudes in ABJM only exist for even number of particles. And the even number I will typically write as n equal to 2k. Secondly, it's a theory of massless particles. Which will allow us in a few minutes to use 3D spinor helicity formalism. And lastly, a bit of a technical note is that the amplitude split up into topologically distinct branches. For today, we're only going to be focusing on the so-called positive branch. But the other branches can be obtained from the positive branch through so-called parity operators. Now, the ABJM momentum amplitude, like I said, lives in the space of 3D spinor helicity. I assume everyone is familiar with four-dimensional spinor helicity, but just to quickly summarize how the 3D story works is we write our momentum p mu, our massless momentum p mu, as the outer product of lambda alpha and lambda beta. So in 4D we would have lambda lambda tilde, we would have two different spinors, but in 3 dimensions we only have one. It's the same lambda. And we can use this to define the standard Lorentz invariant brackets, which is just the determinant of lambda a, lambda j. Right. Furthermore, we'll do something slightly unconventional from the four-dimensional point of view, if you're familiar. But we will take the particles alternatingly incoming and outgoing. So that means that momentum conservation for us means that sum from I equals 1 to n minus 1 to the I lambda I is equal to 0. Now, so when I talk about 3D spinor helicity space, I mean the space of n such lambdas which satisfy this momentum conservation. And with that, we can now define the ABJM momentum amplitude. Which I will denote OK. The subscript k is a number of particles divided by 2, which is a collection of points in 3D spinor helicity space which satisfies, first of all, that the brackets I plus 1 are positive. Secondly, the planar Mandelstam variables, so pi plus 1 plus up to some pj squared must be greater than 0. And a series of angle brackets 1, 2, 1, 3, all the way up to 1n has exactly k sine flips. And the reason that we care about this geometry, as I have defined it here, is that the canonical form of OK is the n equals 2k ABJM tree-level amplitude. Right. So that is a very concise definition of the ABJM momentum amplitude. So far the introduction. Might be a good time for questions if there are any. And otherwise, yes? So k-sign flips means, so these angle brackets will be real numbers. They can be positive or negative. For example, we know from this first condition that 1, 2 has to be positive. So if I just write down this sequence, then there will be some plus, minus on the signs of these things. And if I just count how many times does the sign change, how many sign flips are there, this has to be exactly k, where k is n/2. Yes, there is an associated ordering to the particles. For the tree level, we can assume this to be like some color ordering, essentially. But for the loop level, we do assume planarity as well. So there is a distinct notion of ordering for the particles. Right, now for the main part of the talk, I'm going to be talking about geometries for one loop integrands. So what I've just defined as a geometry for the tree level amplitudes in ABJM theory, we're now going to be interested in the one loop integrands. And without giving a proper definition, I'll just make the claim that there exists a loopy version of the ABJM momentum amplitude, which I will call OK with a subscript L for the number of loops. And this is now not a subset of the space of 3D spinnericity variables, but of the set of spinnericity variables together with L loop momenta. Now this lambda, these the spinnericity variables, they have to be in the tree level, so they have to these lambdas have to satisfy the exact same sign flips and positivity conditions that I just wrote down. Now these L's also satisfy some positivity / sign flip conditions. But I don't think it is too illuminating to write down specifically what these properties are. And we'll see a better way to do things in a few minutes anyway, so I'm not going to focus on that too much. I just wanted to make the claim that it exists. And if we properly define this thing, then the canonical form will give us the L loop integrand. Now we're going to be focusing on these loop geometries and these integrands from the idea of chambers and fiber geometries. For which I will have to introduce a projection map, which I will call pi, and we'll focus on the one loop from now on, which maps the one loop ABJM amplitude to the tree level ABJM momentum amplitude, and which sends some lambda and a loop momentum simply to lambda. So it just forgets the entire loop level structure, essentially. Now it is then clear that the fiber, so the pi inverse of the lambda, the inverse of the projection map, pre-image, encodes the loop level structure, right? Because the image encodes the tree level and the entire thing encodes the tree and loop. So the way to imagine this, let me schematically draw our OK. So this is our tree level ABJM momentum amplitude. And for each point lambda inside, there is an associated fiber geometry. And this fiber, for example, for this point, can look like a prism. And for a point here, it can be a completely different type of fiber. It can be a tetrahedron. But if I take a point close by this one, I might get a slightly different tetrahedron, but I will typically still get a tetrahedron. And this is the idea of chambers. This suggests that we can break up our tree-level geometry into different chambers. So which I will note, for example, C1, C2, and C3. And they're defined in such a way that inside a chamber, when I take 2 points and I look at what their fiber geometry looks like, they will be the same. So inside a chamber, we have the same associated fiber geometry. And what is important about that for us is that this implies that the fibers have the same canonical form. And this allows us essentially to write the entire one loop geometry as a product of the sum over all chambers, the chamber times the fiber. And this is reflected in the canonical form. So the canonical form of the one loop ABJM momentum amplitude, so this is the one loop ABJM integrand, can now be written as a sum over all chambers. The canonical form of the chamber wedge, what I will call the one loop form of the chamber. So the canonical form of the chamber is really just the canonical form of this region of our spinor-elasticity space. And what I call the one loop form is the canonical form of the associated fiber to this chamber. So in this case, the canonical form of a tetrahedron. So this is one of the key ideas. Yes? Yes, they will converge on something. Yeah, it will be a degenerate case, but yeah. No, this is, in this case, it's just, this should not be taken literally. This is just for... Yeah, no, I just took random shapes just for illustration. These are not the type of shapes that you actually see in the real world. So this allows us to write the full one loop geometry in a way that the tree level and the loop level factorize. So this was an observation first made by He, Wang, and Kyo. So it is these fiber geometries and their associated canonical form, which will be the main topic of our discussion today. Yep. So they are spurious boundaries. They're not real boundaries of the amplitude, and they don't correspond to singularities of the tree level amplitude. But you can define them, definitely. They are just some, you can impose some additional constraint, and you can just study this exactly at the tree level. We know what these spurious boundaries are, what their equations are, and you can just try to triangulate the tree level amplituhedron using these hypersurfaces. Mm-hmm. Yeah, I think so. It's conjecturally always a positive geometry with all the properties that positive geometries have. This is just a particularly nice way of triangulating it. But you can study the entire thing as a whole as well, if you prefer. So on the boundaries of the fiber, there will definitely be singularities of the integrand. At the walls of the chambers, no, there shouldn't be any singularities. There's a spurious. Right. So we're going to be studying these fiber geometries and their canonical forms. Let me keep this. And we're going to be studying these fiber geometries in dual space, in the Minkowski space of dual momenta. So just a reminder by what I mean by dual space. We now encode our scattering data in a set of endpoints in three-dimensional Minkowski space such that xi plus 1 minus xi is the momentum pi. So this is, if you have ordered particles, this is a common way to trivialize momentum conservation. Now in our case, we're dealing with massless particles, so p squared is equal to 0. Which in this dual space means that xi plus 1 and xi are light-like separated. So if you give me some point lambda in the tree level ABJM momentum amplitude that specifies for us the momenta of the particles, I can translate this into what we call a null polygon. So that is a polygon with n vertices, where all the edges are light-like separated. So I've given here simple examples for 4 points and 6 points. For 4 points, you have x1 through x4, and the black lines indicate that they are segments of light rays. So x1 and x2 are light-like, etc. Sorry, say again? Yes, we are switching to planar, yes. Yeah, it's all planar, what we're doing today. Now, if we start from a lambda in the tree-level ABJM momentum amplitude, when we can't get every single type of null polygon, there are a few properties which have to be satisfied. And the important ones are that, first of all, xi minus xj squared is positive for non-adjacent I and j. For adjacent I and j, it's of course 0. But for example, x1 and x3 will be space-like separated, positively separated in my metric. x2 and x4 will be space-like separated, etc. And secondly, something that you can already see in the pictures is that, for example, x4, time flows up in these pictures, is to the future of both x1 and x3, and so is x2. And in general, the even indexed x's are in the future of the odd indexed neighbors. Right. So those are properties that the null polygons generated by the tree-level ABJM momentum amplitude satisfy. They're not quite sufficient conditions, but they are necessary. And they're the important ones for today. Sorry, say again? Yes, yeah. Because for the non-neighbors, they will be positively separated by the first point. It's they're space-like, so there's no clear notion of future. I'm not sure. It's what you Yes, it's just about neighbors, yeah. All right, so we're now almost ready to discuss these fiber geometries in this dual space. I just have to make two quick definitions. So we take some point P in our Minkowski space, and then we define NP as the set of all points in Minkowski space which are null separated from P. And I define NP plus as the set of all points in Minkowski space which are positively or space-like separated from P. So the first one is essentially just the light cone of P. And the second one is the subset of Minkowski space, which is space-like separated from P. Now, with this, we ask a relatively simple question, namely, what is the region of Minkowski space which is space-like separated from all the x's? So in the definitions that I've given here, this is the question: what does the region nx1 plus intersect up to nxn plus? What does this region look like? So let's, for example, look at the 4-point case. I'll try to draw it. So we have our null polygon, and to each of these points in the null polygon, we can attach a light cone, right? So for this point x1, the light cone has to pass through the points x2 and x4 by definition. So the light cone might look something like this. And you can imagine attaching such a light cone to all the 4 points. And then the question is, what is the region that is outside all of these light cones? Right? So clearly, if I go far enough up to the side, like a point here or a point there, they will be satisfied. It will not be in any of these light cones. But interestingly, there's actually also points that are sort of inside of the null polygon, which satisfy this property. So actually, this intersection of the region which is space-like separated from all the x's, it very naturally splits up into two parts. A compact part, which I will call delta, and a non-compact part, which I'll call delta bar. So this delta is sort of the compact part, which lives sort of inside the null polygon, and there is a non-compact part, which lives outside, and it goes off to infinity. And I'll use this x with an arrow on top to abbreviate x1 through xn. So what does it look like for these null polygons? The delta will look something like this. So all the points in these orange regions will be space-like separated from all the x's. And these deltas, these are exactly the fiber geometries which we are after. Right. So to recap, we start from a point in our tree-level ABJM momentum amplitude, which defines for us a null polygon in dual space. And then we simply ask, what is the region in Minkowski space which is space-like separated from all the corners of this null polygon, and that defines for us these fiber geometries delta. So let's look at these pictures for a little bit, just to get some geometric intuition for what they look like. So you can see by just staring at the left one that this is clearly some curvy version of a tetrahedron. Right? The one on the right is maybe a little bit more difficult to see straight away, but if you stare at it for a bit, you'll see that it is combinatorially equivalent to a cube. It's a curvy version of a cube. And furthermore, we see that there is two different types of vertices which appear. So first, it always has the vertices xi. The xi's of the null polygon will always be vertices of our fiber geometry delta. But we see in the right that there's also a new type of vertices which appear, which I have colored in red, labeled q plus 135 and q minus 246. And they are defined as a triple intersection of light cones. Now, in general, 3 light cones will intersect in two points, which I will distinguish with a subscript plus or minus. So I will call them q plus ABC and q minus ABC. And the plus and the minus essentially depend on the orientation of the simplex made by XA, XB, XC, and Q. So these are the type of vertices that can appear, the XI and these triple intersections. But not all the triple intersections which you can define will actually appear as part of the geometry. And if we just look at this picture, because of the alternatingly future and past of the even and the odd axis, that the x evens are to the future of the x odds, you can see that the facets of this geometry, the codimension 1 boundaries, they're of course defined by light cones of the axis, but they're always the future light cones of the odd axis, so the future light cone of x1, x3, and x5, and the past light cones of x2, x4, and x6. And these vertices Q plus and Q minus, they are defined as triple intersection of these facets. And they can either be 3 past light cones intersecting or 3 future light cones intersections. So the only vertices which we see are of the form Q plus ABC when all 3 of A, B, and C are odd, or Q minus ABC if all 3 of A, B, and C are even. You will never get something that is Q odd, odd, even as a vertex of the geometry. And furthermore, like I said, these are curvy versions of tetrahedron and a cube. And I already mentioned at the beginning that these are examples of 3-dimensional simple polytopes. And this turns out to be completely general. The delta will always be some curvy version of a simple polytope. So I don't have the definition of a simple polytope on the board anymore, but remember that just means, in the 3-dimensional case, that every vertex has 3 facets adjacent to it. And in this case, that is fairly obvious. So the vertices Q plus minus ABC, by definition, have the facets NXA, NXB, and NXC adjacent to it, by definition of what these are. There's always exactly 3 facets meeting at this vertex. And secondly, also the vertices xi, as you can see in the picture, have 3 facets incident to them. And in fact, the xi are completely defined by the intersection of the light cones of xi minus 1, xi, and xi plus 1. So both the Q pluses and the x's all have 3 facets adjacent to them, which sort of validates my statement that they are curvy versions of simple polytopes. Now at the top right, I have still the formula of the canonical form of a simple polytope. So there is a general way that we can find the canonical form of a simple polytope by summing over the vertices. So we are very tempted to try to write the canonical forms of these objects also in a similar way. Right, so if we just take this formula and we just continue by analogy, we would, so the d logs of the f's means that to each vertex q plus minus ABC, we would associate the canonical form, or sorry, the differential form, d log of y minus xa squared, wedge the d log of y minus xb squared, wedge the d log of y minus xc squared. And for shorthand, I will write this as omega subscript ABC. Right? So this is the d log of all the facets at the vertex q plus minus ABC. And similarly, for the vertex xi, I would associate omega I minus 1, I plus 1. Right? Because those are the facets at the vertex xi. So if we just take this formula and we substitute this in, we arrive at a naive guess of what the canonical form might look like. So we have some term which comes from the contribution of all the n xi's, and then we have the sum over all the vertices q plus and q minus in the geometry. So let's say q plus ABC in delta omega ABC minus the sum of ABC. So this is now a sum by q plus in delta. I mean the sum over all q plus ABCs, which are vertices of delta. So this is now a sum over all the vertices, and we associate these forms to them. And I've already fixed the relative signs to ensure projective invariance. So this would be a naive guess. Unfortunately, it is wrong. For an obvious reason, and that is that the residue as y is equal to q plus minus ABC of this omega ABC is always equal to 1. So for both q plus ABC as for q minus ABC, it will have a residue equal to 1. But recall, when I was introducing positive geometries, I said that there can only be poles at the boundaries of the geometry. And if we look at this example on the right here, we see that only q plus 135 is a vertex of the geometry, whereas this guess would also have a pole at q minus 135, which is not a part of the geometry, and therefore this can't be the correct answer. So the resolution to this problem is to introduce triangle integrands, omega triangle ABC, which I define as plus minus the d log y minus xa squared over y minus q plus minus ABC squared So I define this canonical form, omega triangle ABC, which, much like this omega ABC, also has a residue at both q plus and at q minus, but importantly, it will have it with an opposite sign, such that the combination omega plus minus ABC, defined as omega triangle ABC plus or minus omega ABC, will only have a residue at q plus for omega plus and at q minus for omega minus. So we can use this to sidestep the problem that this guess has too many residues at some q's which are not part of the geometry. Instead, these are the correct forms to associate to the vertices q plus ABC and q minus ABC. So the correct canonical form, which we arrive at if we make that substitution, is that the canonical form of delta is equal to still the sum over all the xi's. The xi's don't have this problem because they're uniquely defined by the intersection of the light cones of xi minus 1, xi, and xi plus 1. There's only one solution here. So those contribution will just keep as they were. And for the vertices q plus and q minus, we now associate this omega plus minus. So this is the general formula for one of these fiber geometries delta. And this is a very powerful formula because once you know the vertices of delta, then you immediately can write down what its canonical form is. So all we have to do if we want to find these, the canonical form of these fiber geometries is study their geometry, see which vertices are part of the geometry, and we can immediately write down the correct formula. So recall, in this picture, if we want to write the full one-loop integrand, or the canonical form of the one-loop ABJM momentum amplitude, what we have to do is we have to sum over the chambers, the canonical form of the chamber, which is the canonical form of the fiber, right? So what we have just done is I've given you a neat formula for finding the canonical forms of the fibers. But to find the full answer, we still have to sum over all the chambers. So for the full integrand, we have to sum over all chambers. Luckily for us, there is a particularly simple classification of all the chambers due to these fiber geometries. So let's start a little table here. So the number of particles and the number of chambers. When the number of particles is equal to 4, there's only one chamber in the 3-level ABJM momentum amplitude. The number of particles is 6. There's also only one chamber. So what that means is that no matter which point in the 4-point or the 6-point ABJM momentum amplitude we take, the associated fiber geometry, the delta, will always look like this or like this, respectively. This is no longer the case at 8 points. At 8 points, we find that there is 4 chambers. Here's an example of what one of them can look like. So as you can see, still, of course, the x1 through x8 are vertices of the geometry. There's still the null polygon in there. But there is different choices for which q's can be part of the geometry. And there's 4 different sets of choices. So the possible choices, I've listed them on the side. We have Q135, 157, 246, 268, 135, 157, 248, 468, 137, 357, 246, 268, 137, 357, 248, 468. The last one is the one that you see here. And there is, if you stare at this list for a little bit, you'll notice that there is actually sort of a natural way that you can memorize this. So for example, the first one, if we draw 2 squares, one of them I'll label with the odd particles, so I'll label 1357, and the second one I'll label 2468. Then, if I triangulate it like this, you'll see that we have triangles 135, 157, 246, and 268. Exactly the vertices that we see in the top row there. And the other 4 also correspond to triangulations of 2 squares. And this turns out to be a very general story, actually. In general, the chambers are labeled by triangulations of two kagons. So we have one kagon which has all the odd particles on the corners, and one kagon which has all the even particles on the corners. And all possible triangulations of these two kagons labels all the possible chambers. And the triangles in these triangulations, again, exactly correspond to the vertices, the red vertices that we have in our geometry. Now, this turns out to be more than just a way to remember things. These triangulations of two kagons actually have a relation to the geometry that we're drawing. They are, in a precise sense, dual to our geometry delta. And what I mean by that, so let's look at the case that you have on the board. So that is the bottom one here. If I draw the dual of these diagrams, so 2, 4, 6, 8, 1, 3, 5, 7. So these are the dual of the triangulation of the two squares in this case. You can see that these, what I drawn in red here, is actually part of the geometry. So this is the point Q137. There at the top, you can see that there is edges incoming from X2 and X8. There is an edge going to Q357, and from Q357, there's edges going to X4 and X6, right? And the same for the other one, but at the bottom. And to make this even more precise, if we take these two kagons and we embed them in three-dimensional space, and we connect the corners I and I plus 1, we find exactly the one skeleton of the dual geometry. So per illustration, let's look at the 6-point case. So recall, I said the 6-point case is a curvy version of a cube. Now the dual of a cube is an octahedron. And now if I draw the two triangulation of two kagons, so in this case, the triangulations of two triangles, the triangles are of course already triangulated, so there is no more lines that I add to them, which is the statement that there's only one chamber for n equals 6. And now we connect the corners I to I plus 1. So I connect 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 1. And if you squint a little bit, you'll see that this is exactly the one skeleton of an octahedron, the dual of the cube. Now in general, a kagon, the number of triangulations of a kagon is counted by the Catalan numbers, so we can finish this table by saying that for a general 2K case, there will be CK minus 2 squared chambers, where CK label the Catalan numbers. And furthermore, just to emphasize, we see the way that I've constructed these triangulations of two k-gons, and the skeleton of the dual means that there are only ever triangles. All the faces of this geometry are triangles, and that's exactly the statement that the delta geometries are simple. That means that every vertex has 3 adjacent facets. So what I've done now is I've given you a complete classification of all the chambers which appear in the ABJM momentum amplitude, and particularly I've told you which vertices can be part of our fiber geometry delta. And I've also told you that if we know the vertices, then we can immediately write down the canonical form. So this allows us to write down a general formula for the one loop integrand in ABJM theory. So for n equals 2k particles, the one loop integrand will be written as a sum over all the chambers. So the chambers, again, are triangulations of two k-gons. So I will write this as T1 in curly tk odd, T2 in curly tk even. So what I mean with this curly tk is all the triangulations of a k-gon, the set of all the triangulations of a k-gon with either odd or with even labels on the edges, on the corners. So this is equivalent to a sum over all the chambers in the way that I've just explained it. Then we have a canonical form of the tree-level chamber, and then we wedge this by the canonical form of the fiber. And we know, given these triangulations, exactly what the vertices are, so we know exactly what the canonical form of the fiber looks like. So for each triangulation, we just sum over all the vertices that are part of the geometry, the axis, and the triangles, which correspond to the triangles of the even, of the odd k-gon, which corresponds to the q plus ABCs, and the triangles in the triangulation of the odd k-gon even k-gon corresponding to the vertices q minus ABC. So this is about as far as I can go for the one loop without going into the tree-level chambers. But yeah, at the very least, the loop level is sort of completely solved. The only thing that remains is to find the canonical form of the tree-level chambers, but that is not something for today. So this is sort of the final formula for the one loop story. Any questions at this point? Yes. So the canonical form of the tree-level ABJM momentum amplitude is the tree-level amplitude. So there is 2 ways that you can think about this. So either you have to look at sort of the canonical function, which is the part that is multiplying sort of the top measure, and then you have to do just a little bit of machinery to extract the amplitude. It has to do with the Bosonization of the Grassmann odd variables, which you have to integrate out, whatever. Or alternatively, you can just, so it will be a form in terms of d lambda, and we can just essentially directly make the substitution d lambda goes to eta, where the eta are the Grassmann odd variables which appear in the super amplitude. Right. X is, yeah, is the variable. So those are, it's a form in Labdas, for, yes. So should more think of it as a point in the ABJM momentum amplitude specifies the external data. It is not defined by the external data. If you give me a momentum conserving set of Labdas, I can't define for you what is a corresponding ABJM momentum amplitude. The ABJM momentum amplitude is a geometry in the space of all possible Labdas, satisfying momentum conservation. Yeah. You only have to integrate over this last part. So yeah, I think so. So the ones that correspond to real momenta, which should be all of Minkowski space. Yes, it's the integrand indeed. Right. So yes. Yeah. Right. So these constraints, for like I mentioned, these positivity and these sign flip constraints, which the loop momenta have to satisfy. So these are not really constraints on, like if you just want to calculate an integrand, they don't really have a physical meaning as far as I'm aware. They just sort of define a region of my kinematic space. So this region of the kinematic space is the ABJM momentum amplitude at loop level, and the canonical form is the integrand. But once you have the canonical form, you're no longer constrained to just look at it in this region where these things are satisfied. You just have the integrand. You already have the integrand, and you can then just do whatever you want with it, essentially. Right, so we have a bit of time left to go over some of the story at 2 loops, and I don't think we'll go any higher. Right. So for the higher loop story, we can define something very similar, just based on the deltas, the one loop fiber geometries, which we have just encountered. We can define a very similar object, which I will call delta subscript L, as the set of L points in delta to the L. So we have L points inside our delta, and we furthermore require that all of these y's are spaced like separated from each other. So we ask the questions, how can we place L points inside of this orange region such that all the points are mutually spaced like separated? That defines for us delta L. And we can then write the canonical form of the L loop ABJM momentum amplitude. So this is just the L loop integrand. Again, as a sum over chambers, canonical form of the chamber, wedge the canonical form of the associated delta L. Now, in principle, you can work with this definition. So this geometry will be a 3L dimensional geometry, this delta L, because we have 3 degrees of freedom for all the y's. But there is a better way of doing things, which is related to what Ross was talking about last week, in an idea which we refer to as vibrations of vibrations. So the idea is very similar to what we've done for the one loop and the tree level. So I again introduce some projection operator, which I will call pi1. And I'll do this for two loop at the moment, which simply maps delta 2 to delta, which takes the 2 points y1 and y2. And just forgets one of them, right? So this is very similar to what we did for the one loop case, except that we're now using the same logic to find the canonical form of this delta L. So the idea is, again, that we can triangulate this delta in terms of chambers. And at each chamber, we have the fiber, so the pi inverse of y. So let me call it the two-loop fiber. As equivalent for all points y1 inside a chamber of delta. So, yeah. The upshot of doing it this way, rather than just studying this 3L dimensional geometry, is that everything so both the chambers of delta and the one loop, the two loop fibers, or the L loop fibers, if we generalize this to higher loops, are all three-dimensional geometries in Minkowski space, which are bounded by light cones of the vertices of delta. So instead of having to consider some 3L dimensional geometry, which becomes difficult to have some intuition for and to do calculations of, we can just do everything for three-dimensional geometries, and everything is a light cone geometry. Everything is bounded by light cones. So let's look at a few examples. For 4 points, we had a curvy tetrahedron. Turns out there is only one loop chamber. So that is to say, no matter where in this tetrahedron I put the point y1, the fiber, the associated, is the orange part, so that is the part of delta which is space-like separated from y1, will always look the same. It will always look like this. Now I can alternatively look at the complement, so the blue part, which is something that is known as the negative geometry, and it has been studied in the literature for both n=4 super-Yang mills and for ABJM theory. Now at two loops, they're simply each other's complement. So I can talk about them interchangeably. At higher loops, the connection becomes a little bit more difficult. But at two loops, you can talk about either the positive geometry, the orange part, or the negative geometry, the blue part. And the blue part is in some sense sometimes easier to work with because, as you can see, it splits up into the part where y2 is in the future of y1 and where y2 is in the past of y1. So you can use some causality arguments. Now for n equals 6, we find that there are 13 one-loop chambers. And the way that we find these is we just take our curvy cube, essentially. So recall the 6-gon with the q plus and the q minus at the top and the bottom. And we just intersect this with the light cones of the q plus and the q minus. So the light cones of q plus and q minus will divide up our geometry into several regions. And these regions are exactly the chambers. So if we look, for example, at the region which is outside of the light cone of both q plus and q minus, you get this geometry in yellow. And that is naturally split up into 6 different chambers. They sort of look like what I have at the top right. And for a point in that chamber, the associated fiber, I've drawn here the fiber of the negative geometry, will look something like this. So it will cut this edge twice and it will cut this edge twice. And then that times 6 rotations gives us these 6 chambers. Now, if we're outside of the light cone of q plus 135, but inside of the light cone of q minus 246, we find that there is 3 chambers. So that is this red region, which naturally splits up into these 3 chambers. That one times 3 rotations. And for a point inside that chamber, so the green point is inside that chamber, the fiber geometry of the negative geometry will look like this. So it will cut one edge at the top twice, and it will cut all 3 edges at the bottom. Now, if we interchange the plus and the minus, we essentially get the mirror image of this. So when we're outside of the light cone of q minus 246 and inside the light cone of q plus 135, we again find 3 chambers, and it just looks like the same one but upside down. Now, I want to point your attention to something. So I've talked about 12 of the 13 chambers now. We'll get to the last one in a second. If you keep looking at the top right, so these are the chambers, essentially, the one-loop chambers. This one is, again, sort of a curvy version of a tetrahedron with boundaries given by light cones. If we go back one, we'll see the same. This red region in the top right is, again, a curvy version of a simplex of a tetrahedron bounded by light cones. And also here, this yellow region in the top right is also, again, a curvy version of a simple polytope bounded by light cones. And we've been talking about this for the past hour, almost hour and a half now. And we know how to find the canonical forms of these curvy simple polytopes bounded by light cones. And so I can actually use the exact same formula, the exact same logic to find the canonical forms of these chambers. Now let's go to the final chamber. Oh. Sorry, say again? You want to tile the tetrahedron? I mean, I'm not sure about that. So the last one is when we're inside of the light cone or time-like separated from both q plus 135 and q minus 246. And the associated chamber, the region of delta which satisfies this, is this purple shape here. And the associated fiber looks like this. So it cuts both 3 lines at the bottom and 3 lines at the top. However, for those of you who know a thing or two about positive geometries, I haven't gone too much into detail, but actually this purple region here is not a positive geometry. At least not in the standard sense. And actually, when we calculate what the associated differential form of this purple region must be, because we know the differential forms of all the other chambers, of the other 12 chambers, we know the differential form of the entire thing, so we can just subtract one from the other to find the canonical form of this purple region. Turns out to be 0. So there are these new things which appear at 2 loops, that we have these regions which are not positive geometries, but we still have to associate a canonical form to it. In this case, the canonical form is 0, which means that if we go to higher loops, for 2 loops or higher, we can just ignore everything that happens inside this purple region, essentially. But we also encounter at higher loops non-positive geometries, things that are not positive geometries, to which we have associated a non-zero canonical form. So this is something new that is happening at the higher loops, and we're still in the process of investigating these things. So that is about all I wanted to say for 2 loops. So to summarize, what we've done today is I've told you, I've defined for you a complete geometric realization of ABJM integrands for any number of particles, any number of loops, through the ABJM momentum amplitude. And in particular, we have looked at the loop level as a vibration over the tree level, which allows us to look at the loop fibers in the dual space, which turn out to be simple geometries, curvy simple geometries bounded by light cones, which we call light cone geometries. And the fact that they are simple allows us to write the canonical form simply by summing over the vertices. In addition, I've given a full classification of all the chambers which appear at one loop, and together with finding the canonical form that allows us to write down a nice and compact formula for the general one-loop integrand for ABJM theory. Now, for higher loops, I have advocated the point of constructing these higher loop geometries by vibrations of vibrations of vibrations, etc., which allows us to find just the L-loop integrand for ABJM theory simply by studying only 3-dimensional geometries, which are all cut out by light cones. And we have some machinery to study these already and find their canonical forms. So I would argue that that is a big upshot over looking at a full 3L dimensional geometry and trying to extract the integrand from that. And with that, I would like to thank you for your attention. Yes, yeah, so that is how the chambers are defined again. The fiber is again constant. So it is the canonical form of these chambers, which I showed you, wedged with the canonical form of the fiber. And then sum over all the chambers gives you the 2-loop answer. No, so for these 2 triangulations, these label the chambers of the tree-level geometry. For each chamber in the tree-level geometry, we have an associated delta, and these deltas are again split up into chambers where the 2-loop fiber is the same. So there is sort of a hierarchical structure where there is where each fiber develops its new chambers, and for each chamber you have a new fiber, and then that fiber is split up into new chambers, and that each chamber has associated fiber, and in this way you can go up and up in loop level, keeping everything 3-dimensional. So for, yes, essentially we do. So for tree level, we have this classification in terms of odd and even. We don't have a full classification for these 1-loop chambers or higher, but we do know how they are defined. They are defined as our delta, and then we just add all the light cones of all the Q plus and the Q minuses. And that will cut out some shape, and we can investigate using various methods in Mathematica what they will look like. And but we don't have a general classification yet. That is something that we're still working on. So for yeah. So if you know the geometry, then the canonical form is unique up to a constant. Yeah, you can write it in various different ways. You can triangulate it in different ways, but once you know the shape, you know the canonical form. That is sort of the rule. So we do sometimes try to triangulate these geometries in various different ways, but we like to stick to sort of light cones because we sort of know how to work with those. Yeah. We do try that sometimes, yes. Mm-hmm. Mm-hmm. So there are cases which essentially look like a cone on one side and some structure on the other side, such that like sort of locally it can look like a positive geometry, but at some other region of the geometry it can be not a positive geometry. And to those type of things we have to associate non-zero canonical forms. We hope so. That is the way that we're hoping to find their canonical forms, yeah. Yeah. It's barely different, to be honest. It's very similar. But if you can have another number of sign flips. Um, hmm. So I would expect that they exist. I'm not entirely sure. I haven't really looked into that.